Imagine looking up and seeing the universe's biggest secrets staring back at you. Have you ever gazed at the night sky and felt the pull of the unknown? Welcome to the world of unsolved astronomy mysteries that you have never heard before. What lies beyond the observable universe? You are watching Documentary. Join us on this journey through the stars, where every question leads to 1,000 more. Where do the heavy elements in the universe come from? The heavy elements in the universe are formed through various processes that primarily occur in stars and during certain stellar events. In the early universe, immediately following the Big Bang, the extreme heat and density allowed for the creation of the lightest elements, mainly hydrogen, helium, and trace amounts of lithium and beryllium. These were the only elements formed during this period because the conditions did not allow for the creation of heavier elements. As the universe cooled and stars began to form, the process of stellar nucleosynthesis became the primary method of producing heavier elements. Stars generate energy by fusing hydrogen into helium in their cores. In more massive stars, once the hydrogen is exhausted, the core contracts and heats up, allowing for the fusion of helium into carbon and oxygen. This process continues, with the star fusing progressively heavier elements, such as carbon into neon and oxygen into silicon, until it reaches iron. Iron is significant because its fusion does not release energy, meaning that once a star's core is predominantly iron, it cannot sustain further fusion reactions for energy. When a massive star exhausts its nuclear fuel and its core becomes dominated by iron, it undergoes a core collapse, leading to a supernova explosion. This explosion creates conditions of extreme temperature and pressure, enabling the rapid capture of neutrons by atomic nuclei, known as the R process. This process forms many of the heaviest elements, such as gold and uranium. Another type of supernova, known as a Type 1a supernova, occurs when a white dwarf in a binary system accretes enough material from its companion star to trigger a runaway fusion of carbon and oxygen. This explosion also contributes to the formation of heavy elements. Neutron star mergers provide another critical site for the creation of heavy elements. When two neutron stars collide, the resulting explosion, known as a kilonova, produces an environment rich in neutrons, facilitating the R process and the formation of heavy elements like gold and platinum. Cosmic ray spallation is a less common process that contributes to the formation of some light elements. High-energy particles, such as protons and alpha particles, collide with atoms in space, breaking their nuclei apart and forming elements like lithium, beryllium, and boron. Over billions of years, the heavy elements produced in these stellar processes are ejected into space, enriching the interstellar medium. This material eventually becomes part of new stars, planets, and other celestial bodies, contributing to the chemical evolution of galaxies. But as we continue to explore the mysteries of the universe, a pressing question looms over us. Will humans one day have to leave the planet or die trying? There are many realistic threats to humanity on Earth. Some are extraterrestrial, like the potential for space junk crashing into our planet, a scenario not unlike the asteroid impact that wiped out the dinosaurs 65 million years ago. But we also face perils of our own making. Before his death in 2018, the renowned physicist Stephen Hawking surmised that we will have to leave our planetary abode at some point, or risk complete destruction from nuclear war or severe climate change. Hawking wrote in his book, Brief Answers to the Big Questions, "One way or another, I regard it as almost inevitable that either a nuclear confrontation or environmental catastrophe will cripple the Earth at some point in the next 1,000 years. Spreading out beyond Earth may be the only thing that saves us from ourselves. Beneath the vast, uncharted waters of our own planet, a hidden world thrives in conditions that defy imagination. Welcome to the deep biosphere." The deep ocean biosphere is an extreme environment, consisting of bacteria and archaea living in depths greater than 1,000 meters, 3,280 feet. Here, in the absence of light, in temperatures of only 4 degrees 39 degrees Celsius, and under pressures about 40 to 110 times that of Earth's atmosphere, life finds a way. Einstein's general theory of relativity, GR, successfully describes gravity and has been a cornerstone of modern physics. Although it has been proven in the local universe in weak field limits, it remains largely untested in the general strong field cases. This leaves us with a profound question: does Einstein's theory hold true in the most extreme conditions? While Einstein's theory of gravity has passed all tests thus far, we can't be sure that it applies everywhere under every condition, especially in the farthest reaches of the universe. The largest deviations from GR are expected in the strongest gravitational fields around black holes, where different theories of gravity make significantly different predictions. The Big Bang did not immediately produce particles with mass. After the universe cooled to a critically low temperature, an invisible field called the Higgs field appeared. It is this field that gives particles mass. But this is only the beginning of our quest. Most of the mass of protons and neutrons is not due to the Higgs field, but results from a property of the strong force that binds quarks. And the mass of neutrinos is not considered to be associated with the Higgs field. Furthermore, and perhaps most importantly, the Higgs field does not explain the mass of dark matter. Indeed, the unknown properties of the Higgs field still need to be scrutinized before we can solve this massive problem in physics. How does the Higgs field interact with other fundamental forces? What unknown properties does it harbor that could unlock new realms of physics? And most intriguingly, what role does it play in the mysterious dark matter that makes up a significant portion of our universe? Are we alone in the universe? To answer this, we first have to agree upon a definition of life, find the places where life can live, and develop the technologies to enable experiments that can detect life. Powerful telescopes, networks of radio and optical telescopes, and missions to the surfaces of planets in our solar system are advancing these investigations. Since 1992, when the first exoplanet was discovered orbiting a pulsar 2,300 light-years away, over 4,000 exoplanets have been identified. Astronomers use numerous techniques to catalog and assess new exoplanets and the stars they orbit, including methods for radial velocity, transit, direct imaging, microlensing, and astrometry. By analyzing spectra of the atmosphere of these exoplanets, we may be able to tell whether biosignatures are, or could be, present. Will we discover that life is a common occurrence in the cosmos, or will we find that we are truly unique? Is water necessary for all life in the universe, or just on Earth? On Earth, water serves many important functions that sustain life. It is considered to be a universal solvent that supports cellular structure and stability, engages cellular functions such as energy production and conversion and waste removal, and facilitates the movements of molecules like oxygen through the blood. It allows our DNA and proteins to function. It even dictates the shape of our cells, which ensures they operate efficiently. But life beyond the borders of our world may rely on very different chemical components and systems. Scientists believe that if they find liquid water, they will therefore find life. However, finding life elsewhere may not necessitate finding water. There might be exotic life that relies on other solvents, such as ammonia, methane, formamide, or sulfuric acid. The quest to understand the true diversity of life is only just beginning. What other secrets might the universe hold? In conclusion, the mysteries of the universe continue to captivate and challenge us. From the origins of heavy elements to the possibility of life beyond Earth, these questions drive our quest for knowledge and understanding.